Good morning. My name is Samuel Edu Anoche. I work for Goldfields as a strategic planning engineer. I've been with Goldfields for about 4 years now, and I've been using MineSight since then. I hold a bachelor's and a postgraduate degree in mining engineering from Ghana and a master's degree in finance from Birmingham Business School in England. This morning, I would like to present how we have used MineSight as a tool to develop an optimal economic pit outline or pit shell, and then further design the pit using pit expansion tool for life of mine and reserve calculation purposes. Key features of this presentation would be introduction of the mine and location. We'll then move on to do the files preparation for optimization, file 13 and file 15. We'll then move on to look at the input parameters for optimization. And then we'll move on to look at the geotechnical recommendations and how we have applied them in the optimization processes. Location of the mine. The mine is a world-class mining operation. It's a large-scale open pit CIL metallurgical plant. It is for ISO 14001 certified, very good. OSAS 18001 certified, and ICMI certified. The mining rate is about 25 million tons a year, with a processing throughput of 5.2 million tons of ore. That's the mine over here, and it's about 250 kilometers northwest of the capital of Ghana, that's Accra. I think the United States is somewhere here. When I was coming, we traveled all the way. Yeah. The mine sits on the famous Ashanti Belt, which hosts the sister mine Takwa Gold Mines, and also other famous mines like the Anglo Gold Obuasi, Konongo, and Bogoso. That's a pictorial view of Amoanda pit as it stands as at now, slightly filled with water. This is Amoanda pit. The Damang cutback is the main pit at Damang Gold Mine, and we have a couple of satellite pits which mostly feed oxide material to blend with the fresh or primary material that we get from the cutback pit. Currently, the Huni pit, the cutback, and then the Huno are being developed into one super pit. The Amoanda pit is a hydrothermal style deposit. It was based on a $350 per ounce engineered pit shell, and the pit was completed in August 2006. Production statistics, we obtained about 124 kilo ounces of gold from there, 1.9 million tons of ore, averaging 2.07 grams per ton. Obviously, with the current gold price and the updated resource models, it's called for re-optimization of the pit to add to see what the resource or reserves would be like. A process flow for the procedures I've gone through. We shoot off with the MineSight PCL file creation. I won't talk so much about this. We'll come to that later. First of all, the resource model we get from the geologist in CSV format. We actually look at it and examine it to see if everything is right. We have some tests we take. We actually subject this resource model through to see if we can use it for mine planning. From there, we go on to create our block model, file 15, and load the model. We clone the model and add extra fields. Now, these extra fields, like we call conf and others, actually help us to state the reserves in according to classification and material type. That is what we want to do. We always want to state our reserves according to reserve classification and material type. After that, we go on to create our file 13. First of all, we update the tuple. We merge the current as-built with the tuple to form the updated tuple. We create file 13 and grade it to the updated tuple. We then create a new file 13 for optimization. Having done all this, we select the correct file 15 and file 13 in MS Compass and then deplete the model. After depleting the model, we have a model view and check the model, do a few checks and cross-check with the CSVs to see everything is loaded right. After that, we do the input for the optimization. We do visual checks of the pitch shell. Then we go on to design with our good old bit expansion tool. After that, we go on to calculate our reserves. Yeah, that's the PCF file creation. I think it's very familiar to all of you here. I wouldn't waste too much time on that. But the salient feature here is that we always make sure that the model settings are well beyond, the project settings are well beyond the model, so that we capture every piece of the block. That's also about the PCF file creation. The next stage is on creating the block model using procedure P61001.dat. We go through the procedure and then output a report. Normally, we'd want to see the report showing how much of the data has been accepted and reduced. These are some of the checks we do to ensure that we have actually loaded everything. That's a view of the block model loaded. We check the block model, query a few blocks, check it against the CSVs. We put the model view in sections and then try to visually check and see if the weathering codes are all right. The top one you see is the capping laterite, and then the oxide layer, and then a thin transition layer, and then the fresh or primary layer. After developing or creating the model, what we do next is to clone the model and add extra fields like the conv, which we'll need in our reserve calculations. And we use the mod class to build our conv. What we're trying to say here is for a conv of 1, we want to say that if the resource classification is 1, which is measured or proven, and then the P code is 1 to 2, which is either laterite or oxide, we give it a conv of 1. So here we have measured oxide, a conv of 2 will be indicated oxide, and then inferred oxide, and then we have measured fresh, indicated fresh, and inferred fresh. Where a resource classification is 0, we make it waste. Over the years, from reconciliation analysis, we realized that we consistently see about 90% of our grades. So this year, during the life of mine planning, we decided to actually apply a 90% to our grades to be on the conservative side. So what I've actually done here is actually applied a 90% to the grades here using the model calcs tool. It's not matter of a scripting effort like we saw yesterday, but that's just what it's supposed to do. At the next stage, we update the tuple using intersect surfaces tool, the as-built, and then the surrounding tuple to generate the updated tuple. And then we create file 13 and grade it to the updated tuple. After that, this is a model view of the graded surface file 13. Following this, based on the file 13 we have created, we actually create another file 13 for optimization so that we can save the initial file 13. After that, we deplete the block model. By ensuring that the correct file 13 and file 15 are selected in MS Compass. Correct file 13 and file 15 will be selected in MS Compass, and the topo items are also selected. And then deplete the model. It's a model view. We critically examine the model. Normally what we do is query a few blocks with these model items in and cross-check with the CSVs to see everything is loaded right. Try to look at it in various forms, sections. That's the model looking below the surface. This is showing the model completely depleted. This is the mine out area with all the model items taken out. The ones we see here are just surface blocks. This shows a lateral extent, a full extent of the model below the surface. That's the topo made transparent, just so we can see how it actually shows below the surface. Now, these are the techno-economic parameters that we feed into optimization. We have our gold price, our selling cost. We deduct it from the gold price to get our net gold price, which feeds into the optimization. We have our fresh material cost, processing cost, our oxide processing cost. And then also we have our mining cost here, the reference mining cost here, and then how the cost increases as we go down the benches. Actually, we used a different application for this calculation. And then these are also the geotechnical parameters that feeds into the optimization. We run a pit slope assignment in file 13, and then begin to go through the panels for optimization. A good feature around this here is over here, when we're running optimization for reserves, we are able to set the inferred materials to NA not applicable, so they won't be added to the reserves. But then when we're running resource, we can set it to use and then include them in the resource calculations. So we set this panel up this way. And then also, this is where we input our variable mining costs as we go down the bench. And that's our discount rate for optimization. Now, the geotechnical recommendations that we get is set that using complex slope by azimuth always works out. Not always, but for this particular deposit, it works out better for us. For a P code of 1, laterite and oxide, the eastern side, the slope angle is about 25.1. For the western side, that is 165 to 345. This azimuth, the slope angle is 24.3. At Damang, Amoanda, what we see is the slope parameters actually change according to material type and then according to azimuth. So we input these parameters in this way. For the oxide material, the eastern, these are the slope angles, and then the west, these are the slope angles. We go through all that. And then run pit optimization to generate our pit shell. This is just a view of the pit shell showing it in various directions. As a pit shell with the resource models showing. And then pit shell, the topo, and this is a shell run at a different gold price. We try to look at it, we try to have a sectional walkthrough of the whole thing to see how the shell behaves. Following this, after we've obtained the pit shell, we go on to do pit design using a good old pit expansion tool. We set it up this way. We digitize the base, input the required design parameters and expansion type that we would want to do. We input the sector patterns at various elevations because they have different geotechnical parameters, and then input parameters for road or the ramps. And then at the end of it all, expand and edit the strings with the pit shell and then the model view as guidance. So that's the design we came out with. This actually shows the pit shell and how the design fits into it. I'm not too keen about showing how much gold we got here, but the interesting feature is how we are able to estimate the reserves according to resource classification and then material type. And then these are the respective grades. That's about it, really. Thank you very much.